us know about the Carnot cycle efficiency. So before going into this Carnot cycle efficiency, we should know how to draw the PV and TS diagram. Okay, this is the pressure volume diagram, and this is the temperature entropy diagram, TS diagram. Okay, so we can see here from the process A to B is the reversible isothermal process expansion, whereas B to C is the reversible adiabatic expansion, and C to D is the reversible isothermal compression, and D to E is the reversible adiabatic compression. Before going to this PV and TS diagram, let us see this. Here we have a source and a sink. The source is maintained at high temperature, whereas the sink is maintained at low temperature, and is the engine. First, from high temperature reservoir, we can also call it as source or high temperature reservoir. From the heat is supplied to the engine, some amount of work will be done here, and finally it is injected to the sink. Okay. So before this, we should know what is the general formula for efficiency. We know that efficiency is given by the formula work. Our work output divided by heat input or heat supplied. Heat supplied. So that efficiency is equals to the work output is given by the formula heat supplied minus heat rejected. So I take heat supplied minus heat rejected divided by heat supplied. So we can see that here the heat supplied is Q1 and each heat rejected is Q2. So I can take the efficiency is equals to heat supplied I take as Q1 minus heat rejected I take as Q2 divided by heat supplied is Q1. Now I separate these terms. So efficiency is equals to Q1 divided by Q1 minus Q2 divided by Q1. So that here you can see that Q1 get cancels. So that efficiency is equals to 1 minus Q2 divided by Q1. This is the formula for the efficiency. Next, we will go to the different process. We can see that the A to B process, A to B is the heat addition process, and B to C to D is the heat rejection process. Okay, so we will take the formula for this one. So heat supplied. So I will take heat supplied from the process. We can see that from the PV diagram. So I can take heat supplied from the process A to B. So I will take process A to B is heat supply. So we can see that Q1, so we have a formula that is PA dA log E of. So that we can see that here the volume, base volume is VB and this is the smallest volume is VA. So I can take the ratio as VB by VA. So I can take the Q1, the A to B is reversible isothermal process where the heat is added at the constant temperature process. Isothermal is equal to the constant temperature process. Okay. So Q1 is equals to PA dA where we can take that equation. So I can take PA is equals to mRT because you can see that A to B as T1. So as we are considering the unit mass, so M is taken as 1. So PA dA can be written as RT1. So I can take this one and substitute here in the place of PA dA, you can substitute as RT1 log of dV by dV. This is the heat supply formula where the heat is supplied at the, you can see, reversible isothermal expansion. Now I should go for heat rejected as Q2. So now I consider heat rejected. The process, I take the heat rejection process will take place between C and D. Okay, we are taking from C and D. So process C to D, same formula. Process C to D, that is Q2 is equals to, again I take it as first C to D, first process is C starts from C. So PC, VC, log E of. Now we check which is the highest volume we have here. You can see that VC is the highest volume and VD is the lowest volume. So I can take this ratio, that is VC by VD. So now again Q2 is equals to PC VC log E of VC by VD where this PC VC can be written as mR, that is according to the gas equation, P is equal to mRT equation, PCVC can be written as mR. So you can see that C to D is the process where we have a constant isothermal process. So I take it as mR C2. So this one is Q Q2 is equals to, in the place of PC, VC, I can substitute this M R Q2 log E of VC by E. This is one equation. This I take as equation number 1 and this I take as equation number 2. Now here I told that as in the equation 1 I have to take a mass as 1, M is equal to 1 kg per unit. So I can take Q2 is equals to R T2 log E of VC by E. Now we have determined the value of Q1 on the equation, that is the heat supplied, and Q2 is the heat rejection. Now we will go to the other processes, another process. I will go to B2C1 process and A2B1 process. For as I told that for adiabatic expansion, which takes place from the process B to C. So I take the process B to C. Before that, have to remember one formula, very important formula, that is T1 by T2 is equals to T1 by T2 is equals to V2 by V1 to the power of gamma minus 2. This is the very important formula which you already know for the adiabatic process, which already you learned in the basic thermodynamics. Okay. Now I apply the same formula here, process B to C. Now what I write the for adiabatic expansion process, same formula, right? You can see that from B to C. The highest temperature efficacy here is here B to C, PV by TC. First I take the highest PV by TC is equals to, in this form I write this one, TB by TC is equals to, I can write this as VC by VB to the power of gamma minus 1. TB by TC is equals to VC by VB to the power of gamma minus 1. This, now from this TB you can see here TA and TB can be written as T1 because it is a constant thermal process or temperature thermal process. So I can write in the place of TB, I can write that TA is equals to TB is equals to written as T1. Similarly for this one, TC is equal to TD is equal to T2 because it is a constant temperature process. So now TB can be written as T1 divided by, now TC, what is TC can be written as T2 is equals to VC divided by VB to the power of gamma minus 2. This I consider as equation number 3, where T1 by Tt is equals to VC by VB to the power of gamma minus 1. This is the expansion process. Once we are considering for the expansion process, next we also should do for the adiabatic compression process. Now again for adiabatic compression. So from the PV diagram you can take that the process is from D to B. So I take process D to B. Now what I should do is again to take the one A and B. The highest temperature if we consider here, we will get the highest temperature as TA by TD. So I will get the same equation here. So TA by TD is equals to, you know that reverse we should take here VD by VA to the power of gamma minus 1. From the diagram of TS diagram we can write TA can be written as T1 because it is a constant isothermal process or isothermal process constant temperature process. So in the place of T I can write as T1 and in the place of TD I can write T2 to the power is equals to, I can write VD by VA to the power of gamma minus 1. Okay, this equation I write it as equation number 4. Okay, so this is for the adiabatic expansion, this is for the adiabatic compression. Initially we have done for the efficiency formula where the heat supplied as well as the heat rejected. Now see, you can compare these two equations, equation 3 and 4. You can see that one side you have T1 by T2 on the both the sides. So we can equate this, or we can do this. Equation 3 and 4. From equation 3 and 4, we can see that T1 by T2 and T1 by T2 is there, so that we can equate the other two sides. So I can write like this: VC by VB to the power of gamma minus 1 is equal to VD by VA to the power of gamma minus 1. So now here you can check that on the both the side power is gamma minus 1. So I can cancel the gamma minus 1. So now I can take this one as a cross multiplication. I will take VC by VD VC by VD is equals to VB by VA. I can write like this because I am doing the cross multiplication here. From equating from 3 and 4, one side is same as other sides, we can equate that one. So VC by VB to the power of gamma minus 1 is equal to VD by VA to the power of gamma minus 1. So this VC by VD is equals to VB by VA can be written as R. So this R is taken as a compression ratio or expansion ratio. So in the place of VC by VD is equals to VB by VA, we can take it up as a R. Now I'll go to the efficiency formula. So initially I told that efficiency is equals to 1 minus Q2 divided by Q1. Now efficiency is equals to 1, I will take LCM here, same formula I get Q1 minus Q2 divided by Q1. Now we take the values of Q1. Q1 we have efficiency is equals to Q1 from the equation 1. I can write like this from equation 1 and equation 2. From equation 1 and equation 2, I can take Q1 as R T1 log E of VB by VA minus, from the equation number 2, you can take it as, this side I can take it as equation 2, that is R T2 log E of VC by VD whole divided by, again Q1 is R T1 log E of VD by VA. So I will substitute the value of heat supplied and heat rejected in the efficiency formula. Now from this equation, we can see that efficiency is equals to R T1 log of, as I told that VB by VA, in the place of VB by VA and VC by VD, we can take as R. So I take compression expansion is R minus R T2 log E of VC by VD. Again VC by VD can also be written as R. So I take it as R whole divided by R T1 log E of, again VB by VD can be written as R. Now from this equation we can take the T1 this log E R log E R is a common factor. So I write like this, efficiency is equals to R is common, log E R is common. Yes, right. So remaining is T1 minus T2 whole divided by, again in the denominator also I take R log E R common, R log E R common. So I remaining is T1. So now we can see the numerator and denominator. So R log E R log E R get cancels. Remaining is efficiency is equals to T1 minus T2 divided by T1. T1 minus T2 divided by T1. So now again separate the terms. T1 by T1 minus T2 by T1. And separating the denominator. So T1 gets cancels. So you get 1 here. So efficiency is equals to 1 minus T2 by T1. This is the final efficiency of the water cycle. So as I told that for the first process you should take heat supplied equation. For the process A to B heat supplied, C to D is heat rejected, and B to C is nothing but it is a adiabatic expansion. So you should take process B to C, you should take the TV ratio. Again from A to D is the adiabatic compression, where you will take from the process D to A, there also you should take the TV ratio. So after that you should substitute the final equation. So the final efficiency of the Carnot cycle is given by efficiency is equals to 1 minus T2 by T1.